Is it working on YouTube? It is. Nice. All right, we got one last one to check. That is X. We're going to get the Aztec death whistle ready. How's it going, John? All right, I think we're good to go. Working on X. All right, let's blow this whistle and get it started. That is the joyous sound of an Aztec death whistle. No promotional affiliation with Aztec death whistle manufacturers, in case you guys wanted to know. Okay. Yeah, I think it's literally supposed to sound like a screaming person. Okay, so today we got a stream for you guys called ViT Registers. ViT Registers is a paper called Vision Transformers Need Registers. This is a paper coming out of Meta and INRIA, which I think is Institut National something something something, French people. Okay. 28th September 2023, so relatively recent paper here. And yeah, maybe let's just dive into it. This paper is kind of interesting because it's basically they find a little bug in vision transformers, and they kind of show how it's found in a bunch of different vision transformers, and then they propose a little fix for it. So it's kind of similar to some of those other papers. We've read a couple papers, for example, on diffusion models where people find random specific bugs, and then when they actually go into that bug, they end up uncovering a little bit of understanding and a little bit of explainability about what is actually going on inside these models. So I figured maybe we could learn a little bit more about VITs by reading this paper. So let's go ahead. Transformers have recently emerged as a powerful tool for learning visual representations. Transformers is a model architecture that's not just specific to vision or image modalities like video and images, but it's also what people use in language models. So all of your favorite ChatGPT AIs, those large language models, or LLMs as they're called, they're also based on transformers, which are all fundamentally based on this self-attention block. And we're going to go into that self-attention block later in the stream. In this paper, we identify and characterize artifacts and feature maps of both supervised and self-supervised VIT networks. So VIT here, sometimes also people say ViT, right? But that's a vision transformer or a transformer that uses or specifically designed for images. And here they're talking about supervised versus self-supervised. Supervised versus self-supervised is two different ways of training machine learning models. In kind of the easiest way to think about it is supervised is whenever your data set has labels, right? So basically you have maybe a classification data set, training a classifier between dogs and cats, and then every single image that you has a specific label that says this is an image of a dog, this is an image of a cat, and so on. Self-supervised is a different way of training machine learning models where you don't have that supervision signal and you're training with something else, right? You're creating your own supervised signal, right? You're self-supervising your training. A lot of times this ends up being kind of like a masked loss or something like that, where you're maybe cutting out parts of the image and then trying to reconstruct parts of that image. The artifacts correspond to high-norm tokens appearing during inference primarily in low informative background areas of images that are repurposed for internal computations. So the same way that you have tokens in a language model, tokens might represent like little chunks of words. Basically, you break up a sentence into, you could think of it as words, but sometimes like one word might be multiple tokens. Things like spaces, dots, periods, exclamation marks, all have their own kind of tokens. But vision transformers also have tokens. And in a vision transformer, the tokens aren't words, but they're basically these little chunks of the image. So this, you take some image like this. This is an example of a vision transformer. And you see, you break up the image down here in the bottom left into these little patches, and then each of those patches get fed in from basically the same way that you read a book, so from left to right and then top to down, and they get fed in like a sentence, right? So a transformer is a model architecture that consumes sequences of things, right? So there's this ordering of the thing. So at some point, whenever people designed the vision transformer, they decided, okay, let's just order these things kind of left to right and then top down. And this is what a little token is, right? And here you have actually the full kind of block. So this would be one attention block, right? You have the patches come in, you have a normalization, then you have a multi-head attention, then you have these residual connections that come up and can skip around. Sometimes these are called skip connections, or residual connections is another name for them. But basically they allow a little bit of information to flow through without necessarily going into this attention block. Then you have a little feed forward or a multi-layer perceptron, fully connected neural net. We want to call it lots of different names for that. Also has these little skip connections. And you have a bunch of these. So there's going to be a bunch of these blocks kind of stacked on top of each other. So that's what a token is, and that's what a ViT is. The soothing sounds of ritual tribute. I love it, Josh Phillips. Question from Random Thoughts. Aren't vision transformers overkill compared to CNNs for image classification? I don't know if it... I think, like, overkill might not be the right way to think about it. I think you could have a very, very large convolutional neural network, and you could have a very small vision transformer. In the same way, you could have a very small convolutional neural network, and then you could have a very large vision transformer. So I think the model architecture is not necessarily the same thing as overkill. To me, overkill is like more the size of the model that you're using relative to the task. So for a simple classification task, yeah, you probably don't want to use a giant vision transformer. Probably okay with a small vision transformer or a small ConvNet. We propose a simple yet effective solution on providing additional tokens to the input sequence of the vision transformer to fill that role. And this is going to be the actual fix. So the first part of this paper, they're going to kind of show you what this bug is, and then they're going to go into like the actual fix for it. So it's a very pleasing paper because they show you the bug and then they fix it. We show that this solution fixes the problem entirely for both supervised and self-supervised models, sets a new state-of-the-art for self-supervised visual model. Look at that, little state-of-the-art. Everybody loves state-of-the-art. On dense visual prediction tasks, enables object discovery methods with larger models, and most importantly, leads to smoother feature maps and attention maps for downstream visual processing. Okay, so the trick that they find, it works well. Register tokens enable interpretable attention maps. So these are going to be the tokens that they end up adding, right? So the fix that they end up doing is they end up adding these little register tokens. So they'll basically add these little extra tokens here that can include information, but maybe without going too much deeper into that. These register tokens enable interpretable attention maps. This is an attention map right here. This is basically showing you intermediate representations as you go through a transformer. So here inside this attention mechanism, there's going to be this attention map. And if you were to actually look at what the activations in that attention map are and kind of plot them so they're kind of like the same relative size and shape as the image, right? Obviously, you can see each little square, like the amount of pixels in this attention map is not the same as the amount of pixels in this input image, but they're kind of resized here so that you can see that this corresponds to this. So this is like obviously the bee on top of this little flower. Here you have the little gondola in the mountains, and you can see how without the registers, you kind of have these weird, what they're calling artifacts here. Where is it? Artifacts. But you have these weird kind of high norm activations here. Like what the hell are these, right? And that's what this paper's saying is they discovered these, and really what they would expect is that the kind of activations follow this specific objects, right? So obviously the bird would be highly activated. It doesn't make any sense that certain pixels here are highly activated with the bird. So that's what this is showing you here. And then you have without registers, so before bug fix, after bug fix. And these obviously look much cleaner. Although you still have a little bit of weirdness here. Like, why is this there, right? What about this random one down here, right? So you still have a little bit of weirdness, but not as bad as in the before case. Embedding images into generic features that can serve multiple purposes in computer vision has been a long-standing problem. First methods relied on handcrafted principles, so this is old school computer vision. You got scale, invariant, feature transform. But then eventually people did deep learning, and in deep learning, you're not actually hand designing your features. You're basically letting the features kind of bubble up from a pushing just gradients over and over again using some data set, and then eventually you get features that are pretty good, and eventually not just pretty good, but even better than all these handcrafted features that people used to make. Today's common to pre-train a model for a task for which plenty of data is available and extract a subset of the model to use as a feature extractor. So here what they're talking about is that sometimes, especially in the type of work that this group does, so this group of people is the same group of people for that have been doing, I think they did the Dino model, they did the Dino V2 model, they did this paper, so they're all about kind of this self-supervised vision models. And these self-supervised vision models, the purpose of them is that you could then use them, you can cut off the little head that's specific to the task and then put a new head on, maybe for classification or for segmentation or for depth prediction or something like that, right? So you can basically take these models which are pre-trained on this self-supervised vision task and then take just the encoder part, which is the part that you're interested in, and then use them for some downstream task that is more specific to the application that you want. Okay. Allowing for training strong feature models, alternatively, self-supervised methods building on the transformer have attracted significant attention due to their high prediction performance on downstream tasks and intriguing ability of some models to provide unsupervised segmentations. So I think they mentioned this later. I have this paper pulled up, but this is the paper they're mentioning here, this localizing objects. Actually, we'll just get to this one. They get to it. The Dino algorithm is shown to produce models that contain explicit information about the semantic layout of an image. Indeed, qualitative results show that the last attention layer naturally focuses on semantically consistent parts of images. And this is something that you see even in ConvNets, right, where basically the hierarchy of convolution layers, or in this case, attention blocks, follows this kind of semantic pattern where the ones closer to the image, right at the bottom, are more kind of high frequency features like textures, edges, gradients, things like that, versus as you go higher and higher up this vision transformer or higher up this convolutional neural network, or further and further away from the initial input, the features start to become more semantically human, if you want to think of it that way, right? So it's more things like ears and noses and cats and donuts, right? So like as you go up in this hierarchy, you get more interpretability. Here they're talking about interpretable attention maps. Exploiting these properties, object discovery algorithms such as LOST built on top of Dino. Such algorithms can detect objects without supervision by gathering information in attention map. So this is the paper that I pulled up here. This is a LOST paper, localizing objects with self-supervised transformers. So self-supervised transformers is the outcome of something like Dino, right? So Dino is just, you're using a self-supervised task to just train this generic vision transformer, and then in this paper they basically show that you can use the attention maps to train in this case, these are little bounding boxes, so basically a detection model. So you didn't need a labeled data set, right? You didn't need a supervised labeled data set where you said this is the exact bounding box that contains the cat, this is the exact bounding box that contains this bird, and you have some guy sitting there kind of like drawing little boxes on top of your images and then using that to train. So in this paper they were able to basically get this just for free by using the fact that the attention maps in this pre-trained vision transformer already have this kind of like segmentation in there. Okay, so that was Dino, and then Dino V2 which was a follow-up, and both Dino and Dino V2 are basically from this same exact group of people. So you can see here Dino V2, which is this one. It's a lot of the same people. You got Timothy here, you got Piotr here, right? That's the same people in this paper. So Timothy, Piotr, I don't actually know these people personally, but it's the same people. So Dino V2 2023 provides features that allow tackling dense prediction tasks. Let me quickly blow my nose here. Dino V2 features led to successful monocular depth estimation. Monocular depth estimation is just predicting a depth image. Monocular there just means a single image, because a lot of times depth is done with stereo images. So that's why you need this extra monocular there. Semantic segmentation. Segmentation is the task of breaking an image into its little, classifying basically all the different parts of the image, and then have each image kind of has like these boundaries, and then you're classifying it into different things. So the classic example of semantic segmentation is something that you would see in like an autonomous vehicle data set like this, where you're segmenting into like the road, the sidewalk, the building, the fence, and so on. With a frozen backbone, so frozen backbone here, this is kind of referring to what they're talking about here, where you can use this pre-trained dyno, you freeze the kind of lower part of it, right, the backbone part of it, and then you only kind of push gradients that are specific to your new task at the top, right? Sometimes they call that cutting off the head, training a new head. Despite the strong performance, we observed Dino V2 is surprisingly incompatible with Lost. Okay, and this is where the kind of mystery deepens, right? Is that this Lost paper seemed to be pretty good at taking the Dino V1 and using it to do this detection, right? But then when they tried to do the same thing with Dino V2, it no longer worked. So what happened? Something broke between Dino V1 and Dino V2. And this is where the mystery deepens. When used to extract features, it delivers disappointing performance, only on par with supervised alternatives in this scenario. This suggests that Dino V2 behaves differently than Dino. The investigation described notably exposes the presence of artifacts in the feature maps of Dino V2 that were not present in the first version of the model. Okay, so now they're making that connection. Okay, maybe the reason that Dino V2 doesn't work as well as Dino V1 is because Dino V2 has these weird little artifacts, right? Like it has these like splotches of high norm, high activations inside this attention map, right? So maybe that's the real reason. I think they have. Is this an illustration of artifacts? Modern vision transformers, we consider VITs trained. Text supervision. Okay, so here you have a bunch of different vision transformers, and what they're trying to show you here is the Dino V1 versus Dino V2. So the G here just means the size. So these models generally come in a couple different sizes. So Dino V2G, I think, is maybe the biggest one. It's like Giga Giant, or no, Dino V2 Giant, and then Dino V1 Big, I guess, for B. But you can see here how Dino B, if you look at the activation map, for example, of these 4 donuts, it is kind of constrained to the location of these donuts. But if you look at the activation map, or attention map, sorry, for Dino V2, you get that weird artifact pattern where it's like the attention map doesn't seem to be at all kind of like overlapped with the image. It kind of just has these random areas here that are high activation values. So what's going on here, right? What happened between Dino V1 and Dino V2? These are observable using straightforward methods. Applying the same observation, we suggest that Dino is in fact an exception, while Dino V2 models match the baseline behavior. We set out to better understand this phenomenon and develop methods to detect these artifacts. We observe that they are tokens with roughly 10 times higher norm at the output. 10 times higher norm. So that's why it just looks very yellow. This is like a color scheme where this kind of like dark blue color basically means a value close to 0, and then this kind of like light bright color means a value close to the max value. Right, and the norm that they're talking about here is a vector norm. So I got a nice little summary of what a vector norm is for you guys, and also any link that I use in this talk is available here on this GitHub page if you guys are interested in. But basically, a norm just refers to kind of the magnitude of a vector, if you want to think of it that way. And these tokens are effectively just vectors. So they're vectors in some space. So high norm basically means that you could think of it like the length of that arrow is very big versus a small norm, the length of that arrow is very small, right? And there's different types of norms. You have L1 norm, L2 norm, L3 norm, and so on. But these little artifacts, those specific artifact tokens have 10x bigger norm, which is a little bit weird. Luke, this reminds me of the QLoRa guy when he said that massive outliers were more prevalent in larger, better models. Yeah, I think that there's probably a lot of the same effect. I think that the kind of emergent behavior, so Luke is referring to a Tim Detmer's talk where he goes into kind of models that have been quantized, and he notices that the bigger the language model, the more that you see this pattern where there's a huge activation, right? Like one big outlier and then a bunch of very small values. Versus if you have smaller language models, they don't have this same kind of behavior. So there's kind of like a threshold at which point the outliers start to have this outsized effect. And I think that this paper is basically coming to the same conclusion, but with vision models. So I think underneath both of the observation that you're talking about, Luke, and this paper, there's kind of the same underlying truth, which I think is the threshold at which you see emergent behavior. So sometimes people say emergent behaviors, they talk about this, and what they mean is that there's this kind of like almost like a phase transition, like the same way that we have liquid water and then at some specific temperature and pressure, it turns into vapor, right? Like, so if the real world can have this kind of weird transition point, then maybe there exists a similar kind of transition point, but in the space of kind of intelligence when you're using transformers. So it seems like you're getting this scaling or this kind of like intelligence, and then randomly you cross this threshold of total amount of parameters combined with the total data set and some other kind of things that we don't fully understand, and then suddenly it becomes much more intelligent. So maybe there is this kind of liquid to gas kind of transition point, but for intelligence inside transformers, and all of these papers are kind of coming to that same conclusion. Okay, at the output correspond to a small fraction of the total sequence. So obviously here, remember that a vision transformer, right, it doesn't see an image in 2D like this, it's seeing it like a sequence like this. So really they're saying the high norm artifact tokens are only a small percentage of the total sequence or total image. These tokens appear around the middle layers of the vision transformer. Okay, so this also tells you something, right? So it's appearing in the middle layers. This is not appearing at the very bottom, right? So it's not like it's kind of a high frequency effect. It's something that requires a little bit of abstraction before it actually starts appearing. They only appear after sufficiently long training, and a sufficiently big transformer. So you're not going to see this with a small ViT that hasn't been trained for very long. We show that these outlier tokens appear in patches similar to their neighbors, meaning the patches convey little additional information. This is another kind of data point to think about in this mystery, is that these aren't appearing in the center of the image. They're always kind of on the edges of the image. And one way to think about what's going on here is that there is a bias to pretty much every single image data set. Every single image data set that you see generally has what's called an object-centric bias, which means that the thing of interest is almost always in the center of the image, right? So when humans take pictures with cameras, right, you take this picture of this bee on this flower, you're really not going to take a picture of this bee on the flower where the bee is kind of in the top corner and the majority of the image is basically nothing. You're going to center the camera on the image or on the object that you're interested in. So what that means is that pretty much every single image, the outside boundary of it is basically nothing. It's just empty garbage tokens. Basically, they just kind of background, low quality tokens. And we're going to see how that kind of ends up being important, because there's a reason why these outlier tokens only appear in kind of the outside kind of ring. It's because that's the part of the image that has kind of the least information. As part of our investigation, we evaluate the outlier tokens with simple linear models to understand the information they contain. So they're going to take these tokens and then they're going to basically train little classifiers on top of them and see if they can find anything interesting. So this is like some good science here. We observe that compared to non-outlier tokens, they hold less information about their original position in the image or the original pixels in their patch. Hold less information about their original position in the image or the original pixels in their patch. Okay, this observation suggests that the model discards local information contained in these patches during inference. On the other hand, learning an image classifier on outlier patches yields significantly stronger accuracy. Okay, so I think they're going to show you a table of this at some point, but basically they're saying that, okay, we took these outlier tokens and then we tried to train some simple linear models on them, right? And one thing that we tried to do is, can I determine what the position of this token was based on this little artifact? And can I determine what the class of this token was based on this little artifact? And it turns out that they're not very good at position, so they're losing that position information, but they're very good for classification, which means that the little artifact patch is actually kind of like almost like a class token, suggesting they contain global information about the image. We propose following interpretation of these elements. The model learns to recognize patches containing little useful information and then recycles the corresponding tokens to aggregate global image information while discarding spatial information, right? And one thing that's important to realize here is that whenever you're feeding a patches of images like this, or patches or visual tokens into a transformer, you're also adding these little position embeddings. So you see here this part that says position embedding. So it's not just the information of this individual patch, but there's also a little bit of information that you're adding in there that's telling this transformer this is where this patch is from, right? So basically what they're trying to say here is that over time, as you're training this model, it's realizing that, hey, the patch from this position over here in the bottom corner is almost always worthless. So if I see the kind of position embedding that tells me that this patch corresponds to the very bottom corner, I know that this token is worthless. Therefore, I can probably put a little bit of information there that'll help the transformer layer ahead of me, right? And I realize I'm kind of like anthropomorphizing a vision transformer here, and anthropomorphizing model architectures is generally not a good way to do science, but it's just such a I think this paper makes it's a lot easier to understand if you can anthropomorphize the vision transformer a little bit and think of it as trying to like leverage its limited compute footprint to kind of sneak in just a little bit more information kind of through this kind of like pseudo class token into the next layers of the transformer. Question from Khalil. It seems like you can add some regularization to not have the weights exploding. Is it the same thing? Yeah, I'm sure you could probably have some kind of regularization that prevents these kind of activations, but I don't think you necessarily want that because I think these are resulting in the performance, right? So part of the reason these self-supervised vision transformers are useful for all kinds of downstream tasks is because they're able to create their own features from a bunch of data. And it just turns out that the way that those features kind of are kind of made in flesh, right, is that they kind of end up being these weird pseudo class tokens. So if you got rid of these artifacts and didn't give them a different way to kind of come through the model, then you would probably lose performance in your vision transformers. Okay. The interpretation is consistent with an inner mechanism in transformer models that allows performing computations with a restricted set of tokens. In order to test this hypothesis, we append additional tokens that we call registers to the token sequence. And this is going to be the bug fix, independent of the input image. We train several models with and without this modification and observe that the outlier tokens disappear from the sequence entirely. So as soon as you give the little ViT just a little bit of extra scratch paper where it can kind of keep track of things, then it no longer uses its own image sequence or image patch sequence as the scratch paper, right? So a little bit more anthropomorphization there. The performance of the models increases in dense prediction tasks, and the resulting feature maps are significantly smoother. The smooth feature maps enabled object discovery methods like lost to work with the updated model. So again, this lost method, the reason it works is because the original Dino activation or attention maps were basically segmentation maps, right? Like if you look at the original Dino activation map, like this is kind of just like a segmentation of this image, right? You have 4 donuts and then you very clearly have 4 patches here, and that's why this lost method even works. So as soon as you fix this and you no longer have these weird high norm artifacts, then you can go back to using the attention maps as effectively a way of doing dense prediction or something like bounding boxes or segmentation or something like that. Cool. Maybe one more thing here. So they introduced the use of the word register here. So what a register is I have, let me see if I find this, yeah. So I found this little diagram here, and inside a computer you have your CPU, and then you have your GPU and other stuff like that. But inside the CPU, there's a specific type of memory called a register, right? And what a register is basically it's like somewhere where the CPU can store intermediate stuff. So if you think of yourself kind of cooking in a kitchen, right? You have your fridge and you have your pantry, but then you also have kind of a little bit of area in the table right next to you, right? And you're cooking and you need to set down your spatula for a second. You can put your spatula in the little piece of the table next to you so that whenever you need it again, you can immediately grab it, right? So the distance of kind of the different types of memory to the actual CPU is important there, right? And as you go further and further away from the CPU, it gets longer and longer to access that type of stuff, and it gets more and more annoying. And this is something that you deal with in GPUs all the time. But the little storage spaces that are right next to the CPU are called registers, and that's kind of where that name comes from, because in this paper, right, they're adding these little register tokens, and you could almost think of those as kind of analogous to CPU registers. Okay. Problem formulation. As shown in Figure 2, most modern vision transformers exhibit artifacts in the attention maps. The unsupervised Dino has been previously praised for the quality of local features. Surprisingly, the outputs of subsequent Dino V2 have been shown to hold good local information but exhibit undesirable artifacts. So this is the Dino V1. Dino V1 doesn't have this problem. Dino V2 does have this problem. We propose to study why and when these artifacts appear. This work focuses on alleviating the artifacts in all vision transformers while we focus our analysis on Dino V2. Okay, let me take a sip of this coffee. All right. So before we kind of maybe go into this, one thing that... Actually, no, wait. Let's go through this and then I'll go into a little bit of investigation that I did myself. I actually... did a little bit of detective work with GPT, and GPT came to some conclusions, and I was copy pasting some code in here, and it had its own interesting ideas, so I'm excited to show that to you guys. But first, let's kind of go into what the official paper authors investigated. So artifacts are high norm outlier tokens. So high norm, right? Basically think of like these little arrows in your head, like a little vector, except in your head, you can really only visualize like a 3-dimensional arrow, but these are much higher dimensional than that. But then the length of that arrow is the norm, right? So high norm, just think of this big giant arrow, right? Compared to like a normal token would be like a little tiny arrow. We want to find a quantitative way of characterizing artifacts that appear in local features. We observe that an important difference between artifact patches and other patches is the norm of their token embedding at the output of the model, right? So their token embedding, that's the vector, and then the norm is the length of that vector. We compare the norm of the local features given a reference image. We clearly see that the norm of artifact patches is much higher than the norm of other patches. We also plot the distribution over a small set of images, which is clearly bimodal, allowing us to choose a simple criteria for the rest of this section. And let's go to Figure 3. Where's Figure 3? Here we go, Figure 3. Comparison of local feature norms. Here are two different sizes. So Vision Transformer B, and I think the 16 is the number of patches, and then this is ViT Giant with 14. We observe that Dino V2 has fewer outlier patches, whereas Dino does not present these artifacts. So you can see here, this is the norms of this image for Dyno V1 and then Dyno V2, and then here are the high norm ones. And here, obviously in this, all of these are kind of roughly the same value. So this is L2 norm. Remember how there's different types of vector norms. You have L1 norm, L2, L3, L4. This is L2. So you can see how in Dyno V1, all of the activations are kind of the same, right? But in Dyno V2, you have bimodal here, bimodal distribution, right? So you have a bunch of them are this value, but then you have this kind of weird bump over here. So they decided to just kind of arbitrarily say, okay, we're just going to choose the kind of the middle here, and we're going to split it, and we're going to say everything here is these artifacts, and then everything here is normal. And measure the proportions of tokens with norms larger than 150. But there is no, this is just kind of like some random arbitrary value that they picked, right? There isn't like some kind of sacred significance to this 150 L2 norm. Outliers appear during training of large models. We make several additional observations. These high norm patches seem to differentiate themselves from other patches around layer 15 of this 40 layer ViT, right? So they're not present at every single layer. They're only present at the higher level layers, which tells you that they probably represent something that's more semantically kind of interpretable, like ears or you know, saying like something that you would be able to recognize as a human, as opposed to just like some kind of weird like edge filter that you would see at the very bottom of a hierarchy of attention blocks inside of ViT. When looking at the distribution, we see that these outliers only appear after 1/3 of training, so only in the higher layers, and then only later on in training. And then when they looked at the different sizes, so different sizes of ViTs, only in the 3 largest models. So that's kind of what they're showing here. Figure 4, illustration of several properties of outlier tokens, distribution of outlier tokens among layers, distribution of norms in training iterations, and distribution of norms for different model sizes. So here you have, on the x-axis here, you have the layer. So here at the very beginning, this is the layers that are going to be right next to the image, right, that are consuming the image. And then as you go higher up, these are the layers that are closer to your output. So these are going to be your more semantically meaningful layers, and these are going to be your kind of more raw image layers. And you can see here how here they're plotting the norm, and right around this layer 15, this is where you see that break. This is where suddenly you see that emergent behavior where your ViT has learned to use some of the sequence as a scratch pad, right? It's kind of learned to use some of those tokens, of which it has this limited amount of tokens that it's consuming, and it's learned to say, hey, you know what, this top corner here, it's always the sky and it never ends up mattering. I'm going to actually pack in a little bit of extra class information into this little token, because that's going to be a lot more useful than whatever the hell was in this anyways, because it's always going to be some sky shit that doesn't matter, right? So you see here's that emergent. Boom, right there. And then the same thing happens with the number of iterations. So down here now, instead of the layer depth, you have basically the how long you've been training it for, right? So in the beginning, you don't have anything. But then as you train this ViT more and more and more, boom, you start to have that effect again. Here you go. Now you're starting to see the ViT learn to use those tokens as kind of like scratch pad. Same thing here. This is the model size, so you have tiny, small, big, large, huge, and giant. Kind of as a side note, like, I don't know about this, like large, huge, and giant, like, is that immediately apparent that huge is bigger than large and giant is bigger than huge? I don't know who picked those names. Why is the G small, right? Like, why is this lowercase g even though it's the biggest one? That's weird. Okay, so you see how with the tiny, the small, and the I guess base, you don't have this effect, but then with the bigger transformers you do. So this plot to me is kind of the most interesting plot in this entire paper, because it really shows that this is kind of an emergent kind of property, where very similar to what Luke was mentioning with Tim Detmer's analysis of quantized language models, there seems to be this kind of almost threshold where the dynamics inside these transformers changes, right? So my analogy is the kind of liquid water turning into water vapor. There's kind of like a similar kind of change in dynamics where suddenly past a certain amount of training, past a certain size, and past a certain amount of abstraction, your transformers and your attention blocks learn this new behavior where they basically leverage the limited sequence length and they overwrite the tokens that are not really doing anything with information that is useful, such as the class. Okay. Distribution of cosine similarity between input patches and their 4 neighbors. We plot separate artifact pouches and normal patches. Local information on normal and outlier patch tokens. One for predicting position, one for reconstructing the input patch. So outlier tokens have much lower scores, suggesting they're storing less local patch information. And kind of this is just a long-winded way of saying that these patches, these artifacts, are not similar to the tokens around them, right? So like if we go back up to this outlier patch is randomly super high, right? But it doesn't have any, like if you look at the patch around it, this probably corresponds to this like little gray area of the, maybe this is better. So this entire top row of the image is just all just the same kind of like faded green color. And then this token right here, super high activation, but that's not at all similar at all to like the other token, right? Like this token here is almost identical. It's just the same kind of like faded green color, but it has almost 0 activation. So that's what they're showing you here, is that you can just look at the neighborhood around, right? Similarity between input patches and their 4 neighbors, and you can say, hey, something's going on here because this patch should be the same as this patch because they're basically right next to each other, but they're not. So that's another way of kind of confirming that it's not like there's something special about it. High norm tokens appear where patch information is redundant. We measure the cosine similarity between high norm tokens and their 4 neighbors. After the patch embedding layer, cosine similarity is basically, you could think, do I have a nice picture for cosine similarity? So if you go back to my analogy of kind of arrows, right? Cosine similarity is basically how whether these arrows point in the same direction, right? So 2 of these little arrows in your head that you're imagining, right? So you have the norm of the arrow, which is kind of like the size of the arrow, but then you also have the similarity, which is kind of like how similar are those little arrows together, right? We illustrate the density plot. Observe that high norm tokens appear on patches that are very similar to their neighbors, suggests that patches contain, little typo there, constrain redundant information, and the model could discard other information without hurting the quality of the image representation. This matches qualitative observations in that they often appear in uniform background areas. And I think later on they're going to show that it's not just specifically background areas, it's like the rim around the image, because there's that object-centric bias to pretty much every single 2D image data set. High norm tokens hold little local information. In order to better understand, we probe the patch embeddings for different types. So they try to basically train a little classifier on top. They do one that tries to predict the position given that specific little artifact, and one that tries to reconstruct the original information. We train a little linear model on top of these embeddings and measure the performance of that model. We compare the performance achieved with the high norm tokens and other tokens. So position prediction. So predict the position of each token, measure its accuracy. We note that the position information was injected before the first ViT layer in the form of absolute position embedding. So the position information is there at the beginning, right? When you're feeding in this image into this stack of attention blocks, you're not just feeding in the patches, you're also feeding in this position embedding, which is telling the model, here's where I got this little patch, right? So this little patch corresponds to the top left. So this position embedding is basically just a vector representation of like top left, right? And what they're going to basically discover here is that they contain less information, is that information is getting eroded, right? You should, if the ViT wasn't trying to like pack its extra scratch work in that place, you should be able to take that and then basically get the position embedding back, right? You should be able to say, hey, this corresponds to the top left, this corresponds to the top right, but that information is basically getting eroded out. And here we have linear probing on normal and outlier. We also report accuracy of classifiers. Let's go back here. Pixel reconstruction. Train a linear model to predict the pixel values of the image and measure the accuracy of this model. We observe again that high norm tokens achieve much lower accuracy than other tokens. This suggests that high norm tokens contain less information to reconstruct the image than others. And I guess that's what they're showing here. So this is a class token. Then you have the normal tokens and you have the outlier tokens. So the class token is right here, and obviously the class token should be the best if you're trying to train a little extra classifier layer on top of these little patches or little tokens. Obviously the class one is going to be the best, so this kind of is the standard, but you can see here the difference that they're trying to show you here is that the outlier tokens are better than the normal ones. So you see here normal, outlier, normal, outlier. This one's actually huge. Look at that. 18 versus 84. 73, 97. So it's like what they're trying to show you here is that these outlier or artifact tokens are effectively pseudo class tokens. Okay, illustration of the proposed remediation. We add n additional learnable input tokens and then the model uses register. Okay, so that's the problem, is that our anthropomorphized vision transformer is effectively overwriting some of the information in the low quality tokens in order to pass that information forward, and that information is generally something like class or specific things in the image. Like I think they have a better example down here, but yeah, so maybe the spoon or the sugar cube, right? So it's kind of like pretty semantically meaningful information. So okay, we don't want it to overwrite the tokens, so why don't we just give it a little bit of extra space, right? We give it a little bit of extra work where it can do its kind of little scratch work, right? And that's what they're going to do. That's this solve, the bug fix, is that they're going to add these little registers here. Illustration of the proposed, we add n additional learnable input tokens that the model can use as registers. At the output of the model, only patch tokens and class tokens are used, both during training and inference. For each image in a classification dataset, we forward it through DynoV2G and extract the patch embeddings. We choose a single token at random, either high norm or normal. The token is then considered as the image representation. Then we train a logistic regression classifier to predict the image class. I think they're just describing how they got this table here and measure the accuracy. We observe that the high norm tokens have a much higher accuracy than the other tokens. This suggests that the outlier tokens contain more global information than the other patch tokens, or kind of put otherwise, these artifact tokens are kind of like a pseudo class token. I think we can see now where this paper is going. Yes. Hypothesis and remediation. Having made these observations, we make the following hypothesis. A large, sufficiently trained model learns to recognize redundant tokens and use them as places to store, process, and retrieve global information. So it's literally creating its own registers, which is pretty fucking crazy. Like, you know, I'm all about not anthropomorphizing, but like it's hard to not anthropomorphize when you have this kind of like emergent behavior here, which is kind of crazy. Furthermore, we posit that while this behavior is not bad in itself, in fact, it's not only is it not bad, it's probably why you get better performance. The fact that it happens inside the patch tokens is undesirable. Indeed, it leads to the model to discard local patch information, possibly incurring decreased performance on dense prediction tasks. We therefore propose a simple fix of this issue: explicitly add new tokens that the model can learn to use as registers. We add these tokens after the patch embedding layer with a learnable value similar to the class token. These tokens are discarded, and the class token and patch tokens are used as image representations. This mechanism was first proposed by memory transformers. That's kind of cool. Improving translation tasks in NLP. We show that this mechanism admits a natural justification for vision transformers, fixing an interpretability and performance issue. Okay. We have not been able to fully determine which aspects of the training led to the artifacts in DynoV2, but not in Dyno. Okay, so I think that's a good place to look into the little bit of investigative work I did with GPT. So I went ahead and Dino and Dino V2 are open sourced, so you can like literally go into the Dino repo here. So this is a GitHub repo, Facebook Research Dino, and then go here into the Vision Transformer. And then inside the Vision Transformer, you can look at the actual attention block. So this is the actual attention block right here, right? And you see, for example, you have the forward. So this is just initializing the different parts of it here, but then you have the actual forward as you go through it, right? When you're actually passing some input to it and it gives you some output. And you can see how you have these norms. So what is that? So let's maybe break this out and then we can kind of look at what the different parts are here. So let's do this. And then let's do this. So you can see here you have self.norm1. So that's this first yellow brick here. Norm corresponds to this here, self.norm1. Then multi-head attention corresponds to this right here, self.attention. And then you have drop path. Drop path, again, is this little arrow here that goes around and then comes back, right? And then you have another norm, self.norm2, which is this little yellow brick here. And then you have your MLP, which is this blue brick. And then you have drop path, which is this little arrow that goes up like that, right? So, okay, that makes sense. And you can also go to Dino V2. So Dino V2 is also open source. So it's a different repo. You go here, Dino V2. It takes a little bit more digging, but inside the models Vision Transformer, you have the Vision Transformer. And then you have to dig a little bit further. Go here, this block function. You go into that block function. The block function is this. And eventually you get to this, which is the attention block for the Vision Transformer. The attention block for the Dino V2. And it kind of looks pretty similar. You know, you have a lot of the same things. You have these norms, you have your attention, you have your FFN. So they changed it from MLP, now they call it FFN. But it's kind of the same stuff, right? We can see a lot of the same patterns here. Let's see, we can pull up the thing again. We got the forward, which is the method that is important here. You see, first of all, you see if self.training. So already there's kind of a little bit more complication here. You have a different code for whenever you're in training versus inference. So already there's a little bit of weirdness there. Like, oh, okay. You know, that's something that they said. They said that this only appears in inference and not in training. So kind of suspicious that you have kind of this conditional flow here, right? But a lot of the same stuff is here, right? You have your norm. So self.norm1. Here's your orange brick here, norm1. Then you have your attention. Here's your attention. You have the same norm2 right here. You have your MLP right there. And you have your drop paths, right? But one thing that they have here in this Dino V2 is this shit here. What is this? LS1 layer scale, LS2 layer scale. So there's this extra crap here, right? Like you're taking the output of your attention, right? So what's coming out of here, and before you add the drop path, you're doing this LS1, right? So there's something right here, which is this layer scaling, and you're doing the same thing here. Again, layer scaling. I was like, huh, okay, what the hell is that? And here you go. This is the layer scale. So the layer scale is a single learnable parameter, right? So here you have a neural net parameter. So that means that this is going to take gradients. It's called a gamma, and you're basically multiplying by this gamma. Okay. So I copy pasted these different parts in here, and I asked, compare these two different attention blocks. I asked GPT to compare. GPT's like, okay, let me break it down. So here's a couple different things. Here are things that are different, right? So it says the layer scaling. Maybe something's going on with this layer scaling. Let me see. These attention blocks are for different ViTs. All right. So second implementation introduces layer scaling. This can significantly affect the norms of tokens if the scaling factors become particularly large or small. If not handled correctly, it can lead to high norm tokens, which might be the artifacts discussed. I don't know. It seems like a potential way that Dino V2 would be different than Dino V1. It also identified the thing that we identified here, this conditional forwarding. So the fact that in Dino V2, you have this like, if training, you do this, and then in inference, you do this. So potentially that conditional stuff is leading to it. But I copy pasted the layer scale and then asked it like, do you think that the layer scaling is or isn't responsible for these artifacts? And then GPT is like relatively simple, blah, 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 introduces this learnable scaling factor. Let's considering these points, it is plausible that the layer scale can contribute to the observed artifacts. If the model identifies certain tokens, especially in the low informative background areas, the corresponding gamma values might get amplified to increase the magnitude of these tokens. This can lead to the emergence of high norm tokens, which in turn give us the observed artifacts. So I don't know. I thought that was pretty cool. Obviously, like, take this with a grain of salt. This is just GPT kind of like spitting nonsense, and I'm just kind of copy pasting random code in here. But I thought it was kind of clever that you could use GPT to do this kind of stuff here and like kind of act as kind of like a little Sherlock Holmes of model architecture for you. So I don't know. I thought that was kind of cool. That conversation is here if you want to read through the whole conversation. But cool stuff. So, okay, we got these artifact tokens, which are basically being used by the vision transformer to basically sneak in information to the next layer. So let's go into the experiment section of this paper. In this section, we validate the proposed solution by training vision transformers with additional register tokens. We evaluate the effectiveness of our approach by quantitative and qualitative analysis. We then ablate the number of registers used for training and check that they do not cause a performance regression. Okay, so they're going to try a different number of registers because if you recall, they said, okay, we're going to add these registers, but how many registers do we add, right? Like, do we add 1 or 2 or 10 or 1,000, right? So that's what they're going to try to figure out here. As the proposed solution is a simple architectural change, we can apply it to any vision procedure or any training procedure. We train on 3 different state-of-the-art methods for supervised, text supervised, and unsupervised. So here they have 3 different vision transformers. You have open clip, which is going to contain text as well. So clip is a type of contrastive training where you're using both language and image. So it's going to be slightly different than these pure vision. Here they have DIT3 and then Dino V2. We get rid of the artifacts by training models with additional register tokens. We provide additional qualitative results. In order to quantitatively measure for each model, we probe the norm of the features at the output of the model. We report these norms. We see that when training with registers, models do not exhibit large norm tokens, which confirms the initial qualitative assessment. So if we go to figure 7, here is basically the smoking gun of the bug fix, where they show you that if you have Dino V2 and then Dino V2 plus these additional register token kind of slots, you no longer have these artifact outliers, right? So you've effectively gotten rid of the outliers. They're still there, right? That information is still there and available to the ViT, except now it's no longer getting rid of this blue token here, which is just the background. Now it's actually just using an explicit little register path for that information. So bug fix works, right? And it doesn't just work for Dino V2, it works for Clip and it works for DIT as well. Although there still seems to be a little bit of something here, right? Maybe a little bit of something. We've shown that the proposed approach removes artifacts from local feature maps. In this experiment, we want to check that the use of register tokens does not affect the representation quality of those features. Okay, so maybe if you add these register tokens, maybe you just kind of destroy everything, you know? It's like maybe the ViT will just be like, hey, I'm just going to use these little register tokens for everything, you know, and it just kind of starts becoming worse in the other things. We run linear probing, a couple different data sets here. You got ImageNet, which is a very classic classification data set, AD20K, NYUD. Follow the experimental protocol, summarize the performance of the models with and without register tokens. We see that when using registers, models do not lose performance and sometimes even work better. For completeness, we also provide the zero-shot classification performance. Okay, so here's basically the performance of the 3 different vision transformers with and without the register tokens, and you can see how the performance is about the same, maybe even a little bit better. You know, here you have a little bit better. Here you have a little bit worse, but this is interesting here. It's a little bit worse on this depth task. So it kind of tells you something. This is a classification task, and obviously I feel like with the classification, that makes sense that the performance is about the same or even potentially better because you're kind of explicitly using these register tokens, which we know are kind of like pseudo class tokens, So it makes sense that if you give it this extra kind of scratch paper so that it can do its kind of pseudo class token information, it's probably going to perform better at classification, which is what we see here. But the fact that it's a little bit worse with this monocular depth prediction task, that's kind of interesting. It's very interesting. Evaluation of downstream performance with and without registers. Consider the probing of linear probing of frozen features and zero-shot evaluation. We see that using registers not only does not degrade performance, but improves at a slight margin. Okay, and here they kind of are visualizing what these register tokens are, right? So you can see here in this image of the dog, the register tokens are kind of like roughly corresponding to like basically the face, the tail, the paws. So it is kind of roughly a pseudo class token for dog. Ablation of the number of register tokens. Okay, so how many tokens are we going to have? If you have 0, that's effectively doing it with no tokens, and then 16, you have 16 possible tokens. So basically, how many of these little extra yellow register tokens do you have? And you're going to have to balance that with also the total amount of compute, right? So like, even though here you kind of just keep getting better and better, the total amount of, or the more register tokens you have, at some point, it's going to be just so much extra compute that maybe you can't really do it, right? And it starts breaking stuff that way. But here you have segmentation. You have intersection over union is a measure of segmentation performance. Top one accuracy is a measure of classification performance. And then mean squared error is the performance metric for depth estimation. So you actually want a lower is better here. So there's kind of a sweet spot here at around 8 tokens for depth, sweet spot at around 4 for segmentation, and then for classification, the more the better. So it's task specific too, which is kind of interesting. That's generally not good. Generally, when you have something that has task specific best values, that's bad news, because it means that you're going to have to tune or sweep over the hyperparameter value of the number of register tokens in your particular application. We study the influence of such of these numbers of tokens. We qualitatively study the attention maps and observe that the visible artifacts disappear. Performance on downstream evaluations. There seems to be an optimal number of registers for dense tasks, and adding one brings the most benefit. This optimum is likely explained by the disappearance of artifacts, leading to better local features. In ImageNet, however, performance improves when using more registers. Yeah, so classification. The difference here, for example, they say dense task. A dense task is something like segmentation or depth, where you're predicting for every, like, it's a dense, you're doing it over the entire image, right? So for something like classification, your output is just like something that's kind of not related to the image at all, right? Or it is related, but it's like much lower dimensional. It's just like dog, versus if you were to segment, you actually basically have to classify every single one of these little pixels. If you were to do monocular depth estimation, you have to basically give me a depth value for every single one of these pixels. So depth and segmentation are dense tasks versus ImageNet is a classification or not a dense task. Object discovery. Recent unsupervised object discovery methods rely on the quality and the smoothness of local feature maps. By leveraging Dino, these methods have significantly surpassed the state of the art. However, the algorithm leads to poor performance when applied to modern backbones, such as Dino V2 or the supervised ones. We run lost on features extracted in backbones with and without registers. A couple other data sets here. Because of the output feature have different conditioning, we manually add a bias. This results of the experiments are presented in Table 3. Where's Table 3? Right here. Unsupervised object discovery using lost. Okay, so lost is the technique where basically the reason it works is because these attention maps are kind of like segmentation map, like pseudo segmentation maps, if you want to think of them like that. So lost works well with Dino, but it doesn't work well with Dino V2. So now they're okay, well, if we fix Dino V2 with the register tokens, can we use lost with Dino V2? And that's what they're showing you here. You can. So it does fix it. So you go from 40% accuracy to 60%, 26% accuracy to 42%, so it does fix the issue. We observe that adding register tokens makes all models significantly more viable for usage in object discovery. Figure 9, comparison of the attention maps of the class and the register tokens. Register tokens sometimes attend to different parts of the feature map in a way similar to slot attention. Note that this behavior was never required and emerged naturally from training. AGI soon, right? Emergent behaviors, I think, is like the coolest part of machine learning, that there's like these transitions, these phase transitions where suddenly you get this kind of strange new behavior that helps. So look at that. The class token, I guess, obviously represents coffee and the sugar cubes, but then each of these different registers are representing different concepts. This one seems to be representing the cup. This one represents the cube specifically on the plate. This one represents the spoon. This one represents the coffee. So you can see how they're kind of like, I call them pseudo class tokens, but they're kind of like almost like, this isn't exactly a class, right? Because it's like the sugar cube here and the sugar cubes here would correspond to the same class, but they're not. This one, obviously, the one on the plate matters more. So it's like it's more than just a pseudo class token. Qualitative evaluation of registers. Want to verify if they exhibit similar attention patterns. To this end, we plot the attention maps. We see that registers do not have a completely aligned behavior. Some selected registers exhibit interesting attention patterns attending to different objects, while nothing enforced this behavior, their activations had some natural diversity. We leave the study of the regularization of registers for future work. I think one of you guys mentioned something about regularization. Okay, related work. Using pre-trained neural networks for extracting visual features has stood the test of time. CNN models, what else? ResNets, vision transformers. Providing strong visual foundation models with self-supervision, everyone's favorite technique. Dataset biases are not well characterized, yes, yet they drive learning and shape the learned model. An alternative approach consists of not using supervision and letting the model learn from the data via pretext task that is designed to require understanding the content of the images. This self-supervised learning paradigm was explored, this masked auto-encoding, which is actually similar to kind of next token prediction, right? It's like you're basically creating your own supervised learning just that comes for free inherently in the modality of the data, right? Both MAE and next token prediction, the reason you can basically do self-supervision on them, where's my vision transformer, is that in masked autoencoding, you're kind of getting rid of some of these, right? But you know what those are because you know what the original image is. The same way that in next token prediction, you're asking it what the next word in that sentence is, but you already know what the next word in that sentence is because you have that text data. So in both cases, you're basically leveraging the fact that transformers are consuming and predicting a sequence, and you know what that sequence is, right? So that's kind of all self-supervision with transformers. It comes down to the fact that your data set is a sequence, and you can cut out different parts of that sequence. You can ask it what the next thing in the sequence is, and so on. Different approach, self-distillation, strong performance. Okay. Focus our analysis on self-supervised learning, more specifically the Dino. We showed that despite excellent benchmarks, Dino V2 features exhibit undesirable artifacts. This phenomenon is even more surprising, which does not show. Should we tell them that GPT figured out what the problem was? Extending the transformer with special tokens was popularized in BERT. However, most approaches add new tokens either to provide the network with new information or use their output value or something. And I actually went and I looked at some of these. So there's been previous works where they basically, you have these like kind of special tokens. So in the BERT paper, so BERT is one of the kind of older language models. This is kind of an older transformer language model that was popular for some time, but if you actually look at the sequence in BERT, there's these kind of special tokens, these SEP tokens, which are separator tokens. SEP is a special separator token, and then class is a special kind of like class token. So already it's not an entirely new idea, this kind of like adding these extra special tokens that allow for some kind of information to go to the next one or the next layer. And you can see here, this is a different work. This is end-to-end object detection with transformers. This is kind of an older object detection paper. You know that it's old because they still use a ConvNet here as the backbone. But in this one, they also have, in this case, these what they call object queries, but these are special tokens that are basically like areas of the image. Right? They're almost like the anchor boxes, but in token form. So this idea of using kind of special tokens and adding new tokens that have like some purpose is not necessarily new, right? People have been doing this in transformers for a while. Different to these works, the tokens we add no information, and their output value is not used for any purpose. They are simply registers where the model can learn to store and retrieve information during the forward pass. The memory transformer is closer to our work and presents a simple approach to improve transformer models using memory tokens added to the token sequence, improving translation performance. So I had not read this paper, but it basically seems like memory transformer is effectively this paper, but for language or text. In follow-up work, Bulatov addresses complex copy-repeat reverse, extends this line to the vision domain, but observes that such tokens do not transfer well. We do not perform fine-tuning and employ additional tokens during the pre-training phase to improve the features obtained for all tasks downstream. Our study contributes to the following new insight. The mechanism implemented through memory tokens already appears naturally in vision transformers. Such tokens allow us to not create but to isolate this existing behavior and thus avoid collateral side effects. What is the collateral side effect though, right? I think you got to trust the little vision transformer. If the vision transformer is saying that, hey, this background token is actually irrelevant and I'm just going to pack in some class information into that, I think your little ViT is being memory efficient for you, right? You don't need to give it the explicit scratch pad. It's actually being eco-friendly and figuring out that it can do its little scratch work in the limited context, because a bunch of those tokens are actually not that useful. So I don't know if you necessarily need to do this. I feel like you just got to trust that the little ViT is doing it well enough. Okay, conclusion. We exposed artifacts, found this phenomenon to be present in multiple existing popular models, and described a simple method to detect these artifacts by looking at the norm of these attention maps. Studying their location, we have proposed an interaction that models naturally recycle tokens from low informative area and repurpose them into a different role for inference. We have proposed a simple fix consisting of appending tokens to the input sequence that are not used as outputs, and have found this entirely removes the artifacts, improving the performance in dense prediction and object discovery. I don't know about this, because I think what they found is that it doesn't work as well in dense prediction. It works well for classification, but for the monocular depth estimation actually made it worse. So I don't know what the fuck they're smoking here. This is not what their data told them. Right? Like, this is worse here. NYU depth estimation, with and without, seems like it made it worse. I don't know what the hell they're talking about here. Okay, but we know it definitely makes the classification better. Confirming the generality of our solution. Okay, let's scroll down. I think they got some interesting little appendices here. Feature norms along locations. Proportion of token norms with larger than the cutoff value. At some positions, more than 20% of the tokens have a higher norm. So here they're looking at kind of where do these artifact tokens appear, and this is basically a smoking gun for the object-centric bias, right? Where it's very obvious that the artifact tokens are appearing in kind of the ring around the outside of the image, because you don't want them to be here, because here is where your object is going to be. And if you're doing any kind of classification or dense prediction or anything like that, these tokens are going to be important, but these tokens here on the edge are probably not going to be important. So that's where the little ViT is doing its scratch work, which is actually kind of interesting because humans do the same thing, right? Like when you're writing on a test and you do your scratch work in the margins of the test, right? So in the margins of the paper is where you do your scratch work. So This is literally the same thing. It's the little ViT is doing its scratch work in the margins of the image. Propagating unit gradients through a bicubic interpolation. Okay, so obviously there's some kind of like anti-aliasing issue here because the attention maps are not the same dimension as the image, so you're going to have to interpolate that. I guess there's some issues with that. The original Dyno V2, the position embeddings are interpolated from 16 by 16 to 7 by 7. Propagating unit gradients through such an interpolation leads to the following. Okay, so you get this like weird striping pattern, I guess. Since our proposed fix introduces new... Oh, Khalil, you're 100% right. The metric is RMSE. Lower is better. Yeah, okay. I take that back. I'm an idiot. This is lower, but it's better because it's RMSE. Right? I literally said it too. I said it right here. RMSE lower is better, but then over here my brain was thinking accuracy. And they even put the little arrow to let you know as well. So I'm looking like a complete fool. You're right. Thanks for that, Khalil. Complexity analysis. Since our proposed fix introduces new token, it also increases the number of learnable parameters and the flop. So yeah, there's also, you're adding extra crap, so it's going to increase the compute footprint of your model, which is why what you're saying, Khalil, actually is more important, and kind of what I was saying, where it's like maybe adding these register tokens is actually worse because, you know, the margins are there. You know, those garbage background tokens, you might as well overwrite them and then keep the same memory footprint. Why have extra explicit memory for something that your model has figured out that it can use the margins and the little scratch area for? Right? So, I don't know. Illustration of intermediate computations. So it's just showing you how you get the little artifact tokens here, but here you do not. Analysis of lost performance. Adding registers allows us to better obtain discovery performance. Attention maps in the last layer for all three cases. Our approach provides much cleaner attention maps, but cleaner attention maps doesn't necessarily mean anything. You know, it's like cleaner attention maps is useful if you're doing some kind of technique that absolutely depends on the attention map being super clean, like lost. But for most downstream tasks, I don't think you really care a lot about the interpretability of the attention map, right? So I think it's probably okay to have those little artifacts in there and then just be more memory efficient. Without registers, here's your little artifacts. And then with registers. Interesting that it always kind of looks like a little cross. I don't know if you guys are noticing that, but like there seems to be like the artifacts, they're not just individual, like sometimes they're like these weird little like cross patterns. I think that might be just a result of the striping that they're talking about here, this like aliasing. Maybe. I don't know. It could also be the way that the position encoding is kind of like discretized. But yeah, these attention maps look a lot cleaner. Just looking at this crab here. Like, look at this one. This one is fucking weird. Versus this. Without and with. Okay, more fancy images. This is actually a pretty quick little paper, so we might just literally be done right here. Let's see if there's anything I missed in the questions here. UNets and diffusion models are relatively safe. Yes. I think there is a UNet that uses a ViT. I don't know. Did I see that? UNet ViT, transformer UNet? Did someone post that? Yeah, there is a UNet transformer. But, so this here, this UNet would suffer from this issue if it's big enough and it's being trained for long enough. But the UNet that is CNN based would not. So a UNet that is a ConvNet would not have this issue. Registers, get rid of that. Okay. I think that's pretty much it, guys. See, is there anything else that I missed here? Not really. We got the paper. I did find some in here, so this is kind of interesting. So this is the Dino V2 paper, right, which we know has these artifacts, and you can see some of them in the original Dino V2 paper. So, like, if you look at this here, this image of the bus, like, what is this? That's totally artifacts. You know? Look at that. Those are little artifacts, which is kind of cool. But yeah, all right, let me sip some coffee, then we'll summarize, and then we'll get going. Give you this free time. Thanks, Yujun. I appreciate the support. All right, so today we read Vision Transformers Need Registers. This is kind of like a little bug fix paper, you know, but I generally like these papers because I feel like they give you good insight and they kind of give you a deeper understanding of what's really happening inside these models. So in this paper by FAIR, Facebook AI Research, or Meta, that very recently came out, they kind of observed that within the attention maps of a transformer, you have these weird artifact tokens, right? And these artifact tokens seem to be always on the edges of the image in kind of areas where you have background that aren't really giving you very much information. And what they realized is that what's going on is that there's this kind of emergent behavior where a vision transformer, once it gets to a certain size, and I really like this diagram here, once it gets to a certain amount of training and a certain size in terms of just raw parameters, and once you go past a certain level of abstraction, right, so further into it, right, deeper in the model or higher up, depending on your perspective, there's this kind of emergent behavior where the ViT starts packing kind of information into low quality tokens. So here in this image of this teacup, right, you have tokens and patches that contain useful things, but then you have patches like this one here, right? Like this patch right here doesn't have anything in it. It's just like this gray background. And what the Vision Transformer learns to do is it learns to say, hey, I'm going to actually pack like this kind of like pseudo class information, almost like a semantic concept, into this little token here. And I'm going to overwrite that token with this information. So this entire stream, I've kind of been anthropomorphizing it. I call it like scratch work. So it's kind of like using that for like a little bit of scratch work. And it turns out that that's exactly what it's doing. They train some little classifiers on top of these tokens, and they discover that, yeah, they're basically like little class tokens. And the fix that they do for this is they say, okay, well, if we notice that our student, the little ViT, wants to keep doing scratch work in the margins of the test paper, why don't we give it an extra sheet of paper so that it can do its little scratch work there? And that's what they did. They give it this little extra register tokens where it can keep track of its little scratch work. And they show that once you add those little register tokens, you get rid of those artifact tokens. You end up with cleaner attention maps, and then it does improve the performance very slightly on a bunch of different tasks, including classification, depth prediction, and so on. With that said, you know, I really like the paper. I think it's pretty cool. I don't know if that's necessarily a good idea, because I think that, one, adding these little extra register tokens is going to increase the memory and compute footprint of your model, right? It's going to take longer to run inference. It's going to take longer to train. It's going to take more memory to train. And I think that the fact that your transformer is overriding the low quality tokens, that's a benefit. To me, that's like a amazing emergent behavior that your transformer has literally learned that, like, hey, this token is worthless. Let me overwrite it with the shit that matters. So I think they should just leave it as that, because that seems cooler to me. But yeah, overall, pretty cool little paper. If you guys are more interested in kind of the code, I definitely recommend kind of scrolling through the Vision Transformer implementations for Dino V1 and Dino V2 and kind of maybe coming up to your own conclusions as to what exactly is the reason for the emergence of this in Dino v2 versus Dino v1. According to GPT, the biggest suspect is this gamma parameter in this layer scale, but there's no that's definitely not a final answer prediction, right? It could be one of a bajillion different things, and it could just literally be the scale, right? It could just be that Dino v2 they trained it for longer and it was bigger. But yeah, that's it, guys. Thanks, Yujun, Kira, Ed, Luke, Khalil, Random, Josh, Generalist, John, all you guys. I'm gonna blow this Aztec death whistle. Hopefully I'm not awakening the evil spirits every time I do this, but we'll do it anyways.